anything you have for me, anything you worked on, anything you like to see, anything. Okay, in that case, let's talk about two special log functions now, because we did not write those. So they are logx. Of course, that's not how we read it. And lnx. So log means base 10. It's, of course, called common log. So if you don't see a base, the base is 10. And this one is, of course, natural. So this one is base 10, and this one is, of course, base, if it's natural, base E. And as we know, as you see in the graphing calculator, they have their own spot here. E to the x and ln, they share the same key because they are inverses of each other. And 10 to the x and log, they share the same key because they are inverses of each other. So those are the two special. Feeling better? Yep. Good. Okay. Going back and forth with your tests, so I'll give them to you because I may forget. Okay. So we looked at an example in which we determined the domain of the log function. Again, let me show you where we are in the process here. So we finished 4.1, we're in 4.2, and then whatever we can accomplish from chapter 4 today. So that's the target, whatever we can. So let's go back to 4.2 and work on a couple of problems. I want another one with domain. So let's take a look at 78 on page 490, in which we have f of x equals common log of 7 minus x. The same question, we are asked to find the domain of this function. And then I would like to look at a word problem. We know that there are three functions that potentially can create problems. The first one is the square root, the second one is a rational, and this is the third one. These are the three functions that we have to worry about. So what would you write? What do I have to write and solve in order to get the domain of this function? What should I put in writing? I have to show something and then solve it. What do I have to show? What do I have to write? Yes? 7 minus x? Not equal. Greater than 0. Indeed. If it's 0, it will be undefined. We cannot have 0. So when I solve this, I get this by moving 7 to the other side. Then what do I have to write or do or perform? Yes, multiply by -1. So this will be this, and then obviously I have to. Yes. So the domain of this function will be -∞ to 7. Okay. Few properties properties of log function. Just a few properties, tiny ones, and then we'll look at a word problem. Let's discover them. I just don't want you to memorize anything. So let's say I would like to determine log of 10. And you will say, I have no clue. But we know that we can change this into an exponential equation. Remember how? Starting from the base, 10 raised to whatever, this number, equals 10. Well, obviously there is only one answer here. The function is 1 to 1. So the only answer is, say it again, of course, the only answer is 1. So in conclusion, log of A in base A forever, what will this be? 1. What about natural log of E forever? What will this be? You don't have to say anything. What is the base here? E. There is no base of 1. So E raised to what number is E? E raised to what number is E? 1. So please remember, log in the base A, any base of the same number of the base is always 1. Would you agree? Moving forward, we remember this? Log base 2 of 2 is? Log base 10 of 10 is? Log base 5 of 5 is? Yes? We know why. Perfect. Moving on. So that was a little property. Here's another little property. Log base 5 of 1. Let's say we have no clue. Let's change it into an exponential equation, and we'll figure it out. Five raised to whatever is 1. So the base counterclockwise raised to this number equals this number. And there is only one number that does this. 0 indeed. So this must be 0. So log in any base of 1, any base, you name the base, of 1 will always be 0. Log in any base of 1 is 0. What about natural log 1? 0. What about log base 5 of 1? I should have choose. Let me choose 6. 0. Log in any base of 1 is 0 indeed. Very good. Okay, let's look at a log function with transformations, and then we can move on. You can make one up for me. Let's say log base, okay, common log, perfect, of, let's say x plus 3, and let's say minus 2. We start by finding the domain of this function. So the requirement here, let's write the requirement. I didn't write the requirement. Graph using transformations. Graph using transformations. Which base function did I use to create this function? Read it, and you'll see, oh, I used this function. But you have to read it first. If you say absolute value, then you'll say absolute value of x. If you, when you read the function, you say x squared, then you'll have to say x squared. If you say square root, then you have to say square root. But you're not saying any of those, but you're saying log x, right? So the function is log x. Perfect. So what is the first transformation on log x? Yes, awesome. What does that do, and what transformation is it? Excellent. How many? Excellent. Right. Okay. Number 2 is a transformation on number 1. Log of x plus 3 minus 2. What does 2 do to 1? Excellent. Excellent. Downshift of 2. Excellent. Good. So now before we continue, can anyone tell us what to write? We need to write something and solve it in order to determine the domain of this function. Please tell me what I should write. Look at the previous example. It's in your notes. Yes, x plus 3. Not equals. We didn't write equals. Greater than, of course, yes. Excellent. So x greater than negative 3. So sorry here. Of course, this is left 3. My apologies. So the domain is negative 3 to infinity. So please make the correction. It's left 3. Sorry. Good. So then, let's graph the function. Can anyone tell us whether log x is an increasing function or decreasing function? Yes. Why? Because the base is?
Greater than 0.
Then not 0. There is no 0 base. Greater than? It's greater than 1. So because of that, here is the base. Here is log x. It's an increasing function on all its domain. It will always, as a pure log function, will always cross where? At? 1. Exactly. And now we know that this function has a vertical asymptote. Can anyone give us the vertical asymptote of this function? Vertical asymptote is x equals 0. Very good. When we shift the graph left or right, a graph that has a vertical asymptote, what do I have to shift first? The vertical asymptote. Where will the vertical asymptote be now? At negative 3. 1, 2, 3. X equals negative 3, a vertical asymptote. So please now tell me, where does this point move? When we shift the graph 3 units to the left, where does this point move? To which point? Negative 2. Very good. Right here. Excellent. So this is log of x plus 3. Great job. Now, final transformation. You told me that this graph has to be shifted where?
3 left, 2 down.
2 down. Very good. I only need this point. Please give me this point. Tell me where it's moving. Negative 3, comma?
Oh, negative 3, negative 2.
Excellent. It's negative 2, comma, negative 2. Yes. Thank you. Thank you. Thank you. So this is the final graph, which is log x plus 3 minus 2. So we use transformation. Does it make sense that the domain of this function is negative 3 to infinity? Does it make sense that it has a vertical asymptote at negative 3? Any questions? Any questions? Okay, let's look at our problem now. (119). Let's read the problem. Okay. Students in psychology class, took a final examination as part of an experiment to see how much of the course content They remembered over time, and they took equivalent forms of the examined monthly intervals thereafter, between 0 months and 12 months for the next year. The average score for the group, f of t, so that's the average score for the group, after t months, t is in months, was modeled by the function. We're going to copy the function in a minute. What was the average score on the original exam? What was the average score after 2, and sketch the graph. So let's copy the function. The function so this is problem 119 on page 491. We have f of t, it's 88 minus 15 natural log x t plus 1, and t is between 0 and 12. And the first question is original average score. So t is in months. This is the average score. T is in months. I have to take these notes so I don't forget the measurement unit, etc., etc. Now let's look at this function.
Are you sure it was +1? Because I wrote that.
Yes, t plus 1. I'd rather go back and check. Okay, so let's look at the function first. Disregard what it means, what t is, what f of t is. What is the base function here? Just read it and you'll say, it's ln. Very good, natural log. It should be ln instead of, it should be nl, but it's in German, so it's logarithm natural. That's why it's ln instead of nl. Okay? But we have to keep that ln. Good, it is a natural log function. Where does it go? Shifted where? To the left one. Then stretch vertically by a factor of 15. Then reflect with respect to the x-axis. And then we understand the graph quite well, right? So it's natural log x. It's shifted to your left one. It's stretched vertically by a factor of 15. It's reflected with respect to the x-axis. And then up 88. Okay, perfect. So I'm asked to find the original score, average score. What do I have to do? Whenever I'm asked to find the original, what am I really asked to find? Original or initial? Say it again?
Origin.
Yes, but what do I have to do?
Or you find the log first.
So this is the function. We're given this. We're asked to find the average, the original average score. What does that mean? What am I really asked to find? Yes, f of 0, of course. F of 0. Which would be 88 minus 15, natural log 1. But what do we know about that natural log 1? We just looked at natural log 1 a few minutes ago. 0. This is 0. So then what is the average score that the psychology class, the average score of the first exam of the psychology class, initial? How much? Say it again.
53.
But this is 0 times 15, right? So it's 88. Part B. They want us to determine what happened after they took it 2 months later, 4 months, 6 months, 8 months, 10, and 12. We're going to do this. Construct a table. We're going to put 0, 2, 4, 6, 8, 10, and 12. And in the first value, we're going to put 88. The rest, I can't. I have to use a calculator. And let's go to y equals. Let's put in 88 minus 15, natural log in parentheses x plus 1, close the parenthesis. And let's go to second and table and put in the numbers we need. 0, 2, 4, 6, 8, 10, and 12. So let's copy. Let's round them. So 71.5, I'm going to say 72. 63.8, 64. 58.8, 59, 55, 52, and 50. Did we all get this? Did you get something else?
No, I don't know how I got there. So I'll figure it out. Oh, never mind. I figured out how I got there. Problem solved.
Say it again.
I figured out how I got there.
You can use this.
I don't need it.
Okay. Anyone wants to use my calculator? Okay. It's right here if you change your mind. Finally, we're asked to graph this function. No problem. In part C, let's graph it. T goes from 0 to 12. 2, 4, 6, 8, 10, 12. And this, the y values go from 50 to 90. So I'm going to make a break in here of the y-axis. I'm going to say 50, 60, 70, 80, and 90. And I am going to plot the points. At 0 is 88. At 2 is 72. At 4 is 64. And then it's 59. And then it's 55. And then 52. And then 50. Here is the graph. This is the graph of f of t, 88 minus 15 natural log t plus 1, only between 0 and 12. Any questions for me? As you see, for this model, for this situation, real life situation, they couldn't fit anything else through the points. They couldn't fit a square root or x squared or x cubed. Nothing. Nothing worked but a natural log function. Any questions? Any questions for me? Okay, now we can make progress. Everything okay? Yes, Heather, done? Okay, so 4.3. 4.3 deals with 3 properties of log function plus the change of base. Change of base formula. The properties that you are going to see, say it again.
Some difference in the
Power. Yes. What you meant was the product rule, the quotient rule, and the power rule. Correct. Yes. So these 3 properties you will never see. No other function has these 3 properties. You'll never see them again. They are typical to the log function. And the change of base formula is very useful because some calculators do not have the option of putting in the base you want. And you may have to use the 2 bases that we have in the calculator for sure, log, common log, and ln, natural log. Okay, so first property, product rule. When we apply log in any base, it doesn't matter. To a product, I can have 2 factors, 3 factors, it doesn't matter. This changes into a sum of logs. Log base a of x and log base a of y. But this property or rule should be looked at in a dynamic way. What does that mean? This is again a double equivalency symbol, meaning that if I have log of a product, I'll change this into a sum of logs. But if I have sum of logs of two logs, sum of two logs, I can come up with the right-hand side, which is log applied to a product. So let me show you a simple example. Let's say we want to expand log of 2x. Well, this is log of 2 plus log of x. Why? Because 2 is multiplied by x. So we have two factors, 2 and x. So log of 2x is log of 2 plus log of x. The second property, please stop me if you have questions. The second property is the quotient rule. And I want you to come up with this one. So it's log in any base of x over y. What do you think the answer would be?
So log a x times.
What do you think? If the product changed into a sum, the ratio will change into a? Exactly. Log base a of x minus log base a of y. So please pay attention to something that will come back later. If the quantity comes from the denominator, it will have a negative in front of the log. If the quantity comes from the numerator, it will have positive in front of the log. Only quantities that come from the denominator will have negative in front of the log. Last property. And again, only the log function has these properties. Number 3, the power rule. Log in any base of x raised to a power. The power goes in front as a factor. It means that it multiplies log. So as an example, if we have log base a of x squared, this is 2 log base a of x. Of course, I forgot to say here, this goes back and forth. See here the same. Meaning, if I see a difference of logs, I can go back and write log applied to a ratio. If I see a number in front of the log, I know it really comes from the power of x. The last one is the change of base formula, and then we'll practice all of these. Let's say I want to determine log base 3 of 7. And you'll say, well, no problem. It's not a problem, because I know that I can change any log equation into an exponential one. So what should I write? We always start with the base, counterclockwise. Raised to blah equals, yeah. But this time I can't. I have no idea. I don't know what number I raised 3 to get 7. If it's 9, I'll say it's 2. 3 squared is 9. If it's 27, I'll say it's 3. 3 cubed is 27. But if you want me to say what number I raised 3 to get 7, I have no clue. But there is a way to determine this number. Which log do you want to use? Do you want to use natural log or you want to use common log? It doesn't matter. Let's use both. The answer will be only one. If you use natural log, you have natural log of the number over the natural log of the previous base. The same thing if you're using log. Log 7 over log 3. Please understand that this is not the same with this. Some of my students sometimes confuse these two. This one is log applied to a ratio. This one is a ratio of two logs. So these two have nothing in common. or these two. So now, of course, I can do this without a calculator. So let's put in the graphing calculator. So let's use log. No, that's not there. So let's say natural log 7 in parentheses divided by natural log 3 in parentheses. Or if you want to use log 7 divided by log 3, you will get an identical number because there is only one number I raised 3 to get 7. Can't find two numbers that I raised 3 to get 7. But now I want to check this. How will I check this? How will I check whether 1.77 is correct? Here's why and how. So I claim that this is 1.77. I raised 3 to 1.77. What should I get? If 1.77 is correct, what should I get? So here's how we do it with the calculator. So 3 power the previous answer. I don't want to truncate the answer because if I put 1.77, I'm not going to get 7. But if I recall the entire previous answer, when I press enter, I will definitely get 7. But if I write 3 raised to 1.77, I'll get close, but not exactly. Because I rounded down or I rounded up or whatever I did. So I get 6.99, which is not 7, of course. So these are the properties of the log. Yes, please, Jordan?
How did you get the previous answer?
With the second, and the negative sign, it says A and S, answer. So with the second and previous answer with a negative.
Gotcha.
We got it? Perfect. So all I want now for the next few minutes, I would like us to practice. So we want to practice going back and forth and also the change of base formula. So let's start with the change of base formula because it's the easiest. Okay, 72. And get that out of the way. On page 501, we have log base 6 of 17. Now, it is possible that your sophisticated calculators, the new ones, and they do, as you see, they allow you to put in the base you want, but you still have to know the change of base formula. Okay, so they allow you to put in, but the calculator I have, maybe this one does, I haven't checked, but the calculator that I normally use, which is a old-fashioned 84, does not have that option. Okay, so in order to determine this, please tell me which log would you like to apply? It doesn't matter, but you have to be consistent. Top and bottom have to be the same log, either natural log over natural log or common log over common log. So which one? ln. So 17 over ln of 6. This is always the truth or the rule. Natural log of the number over the natural log of the previous base. And we can't do this by hand, of course. We have to determine the number. So we have natural log 17 over natural log 6. In order to check, I will have 6 raised to the previous answer, and when I hit enter, what should I get if this is correct? I should get 17. So the answer is, there in the book, I think they're asking us to use 4 decimal places. 4 decimal places, fine. So I'll say approximately. So this is approximately 1.5812. Any questions on the base or the change of base formula? Or can we continue with expanding and condensing? Using the 3 properties, the property of power, the product rule, quotient rule, and power rule. Do you think we need more of determining using the change of base formula? Are we okay with the change of base? Yes? Okay. So now let's start with, look at problems with expanding. So this time we want to expand log expressions. Expand log expressions. Ready? All right, let's start with I don't want to start with the radicals just yet. I just want to start with a simple example like 21. 21 on page 501. We have log of base b of x squared y. So what they want us, when they say expand, they want us to write this expression with simple logs and apply the three properties that we just learned, till no other property can be applied. Normally we start with a quotient, but there is no quotient here. I have a product of x squared times y, so I have to start with a product. What do we know about log applied to a product? It changes into log base b of x squared and
Minus.
plus log base b of y. So it was log applied to a product, which changes into log of the sum of two logs. Is this step clear? Now, we cannot further simplify this because it's done, log base b of y. But we can further simplify this because there is another property that we haven't used yet that we can apply here or applies here, which is the power rule. So the power, which is 2, simply goes in front of log. And this is it. It is completely expanded. We cannot use, there is no other property that we have to use here. It's simple logs, all properties were applied. Now let's look at something slightly more difficult, the next step, like 27. Any questions on 21? 27, same page. Log base b of x squared y divided by z squared. Now here I see all three properties are applicable. There is a quotient, there is a product, and there is power. Before we even expand this, how many quantities or factors we see at the top? 2. How many factors or products, or if you want the factors, how many factors we see in the denominator? 1, which means only one log will have what in front? The negative sign. Only one log will have the negative sign. 2 factors come from the top, both logs will have positive in front. 1 factor comes from the denominator, only one log will have the negative sign. Ready? We have to apply the quotient rule first. Can anyone tell us what to write?
Log base.
Yes, log base b of x squared y. Exactly. Log base b of z squared. Great job. So we are done with the quotient rule, but now the product rule has to be applicable right here, and the power rule applicable here. So what do I write for the first one? Log base b of x squared, perfect, plus log base b of y minus 2 log base b of z. Awesome. There is only one step left. This is completely simplified. This is completely simplified. We only have to apply the power rule on the first one. So we have 2 in front, log base b of x, log base b of y, minus 2 log base b of z. Again, I cannot stress enough how important this is because we're going to condense in a minute. So notice that there is how many logs with negative in front? How many quantities will go to the denominator when we go backwards? Good. Let's look at the next level now. Too complicated for my taste, but let's do it. 38. Same page, 38, natural log of this big thing, x to the fourth, the square root of x squared plus 3, and everything divided by x plus 3 to the fifth.